Welcome to the Deep Dive. We're the show that cuts through the complex research to bring you the core insights. And today, we're looking at something pretty fascinating. It's this intersection of ancient traditional Chinese medicine, TCM, and well, the absolute cutting edge of AI. We're talking large models, virtual cells, the works, our focus. It's on stroke treatment, a really serious global issue. High mortality, high disability rates, and ischemic stroke, the kind caused by blockages. That accounts for what, 87% of all strokes? Huge number. Now, TCM, it's always had this interesting angle, low toxicity, is centuries of evidence suggesting it works, often lower cost, but scientifically, it's been tough. These complex formulas, dozens of ingredients working together, it's like a black box. Modern science has really struggled to pin down how that synergy actually functions.
Exactly. That's really the core of it. For so long, we've relied on, well, empirical summaries, seeing that it works, but not quite grasping the why at a deep mechanistic level. So this deep dive, our mission today, is to systematically unpack how AI is finally giving us the tools, objective, quantitative tools to decode these mechanisms. We're looking at research showing how AI helps overcome the sheer complexity of the data and also, the subjective parts of traditional evaluation. It's about pushing TCM towards verifiable precision.
Okay, let's start with the basics then, the biology. When someone has an ischemic stroke, what's the immediate chain reaction? What actually happens inside the brain?
Right. It's a cascade, a really rapid biological collapse. The blood vessel gets blocked, right?
Wow.
So no blood supply. That means ischemia and hypoxia, basically the brain tissue is starved of oxygen and nutrients. Instantly, the cells, power plants, the mitochondria, they start shutting down. This energy failure leads to a massive surge of these damaging molecules called the reactive oxygen species, ROS, free radicals. And that triggers overwhelming oxidative stress. It damages everything, proteins, lipids, DNA, vital stuff. At the same time, this whole failure sets off alarms. You get severe neuroinflammation. Key pathways, like NF-key, get activated. And when NF-key switches on, it pumps out inflammatory signals, things like TNF-IL-1. Think of them as distress signals that also cause collateral damage. The whole process disrupts the blood-brain barrier, which is critical for protection, and leads to widespread cell death, apoptosis, necrosis. It's this really complex web of signals going wrong.
Wow. Okay, so it's a complete system meltdown within the brain tissue. But TCM, it doesn't just look at the brain in isolation, does it?
No, absolutely not. That's a key difference. TCM takes a holistic view. It's about restoring balance, yin and yang, qi and blood. It sees the body as an interconnected system. So for stroke, it's not just a brain problem. TCM considers how the brain communicates with other organs, the heart, liver, kidneys, even the gut, which we're understanding more and more is crucial. That's why you see these classical formulas like Buyang Wanwu decoction still used. They seem to work synergistically, intervening subtly at multiple points in that whole inflammatory and oxidative cascade you just described. They're aiming for systemic harmony.
But proving that synergy, scientifically, that's been the real bear, hasn't it? The traditional research methods just weren't built for that kind of complexity.
They really weren't. I mean, think about the standard approach.
Yeah.
Extract compounds, purify them, test them one by one. It worked for discovering single drugs like artemisinin, sure. But apply that to a TCM formula with, say, 50 ingredients. You isolate one compound, you completely miss the interaction, the Groot effect. The whole point is the combination.
Right. You lose the essence of the formula.
Exactly. So researchers tried things like network pharmacology, NP, which was a step forward, definitely. NP looks at multiple targets at once, trying to map the network of effects. It lines better with the holistic idea of TCM, but it's static.
Static, meaning?
Meaning it gives you a snapshot in time,
Right.
like a photograph of the interactions. But biological systems, especially during something like a stroke and recovery, they're incredibly dynamic. Things change second by second. NP couldn't capture that flow.
Okay, so static snapshots aren't enough. We need to see the movie, not just the stills. And this is where AI really starts to change the game, dealing with that dynamic complexity. Let's start with machine learning, ML.
Right, ML is kind of the workhorse here. Its job is to learn from data, find patterns we might miss, and predict things. You have supervised learning, where you feed it labeled data like omics data, genomics, proteomics. You tell it, this data corresponds to this outcome. Algorithms like random forest or SVMs can then sift through this huge multidimensional data and help identify potential drug targets. It overcomes that difficult data integration problem. A key technique here is often QSR modeling, quantitative structure-activity relationship.
QSRR sounds technical.
It is a bit, but the idea is simple. The AI looks at the digital structure of a compound, its shape, its chemical properties, and predicts how active it might be against a certain target. It's like guessing how a key will fit a lock just by looking at its shape, but on a massive scale.
Mm.
It helps researchers prioritize which compounds in a complex formula are most likely to be doing the important work.
Got it. So ML helps narrow down the suspects based on structure and existing data. But then there's deep learning. DL, which you mentioned, handles even more complex stuff, especially these huge networks.
Exactly. DL uses these multi-layered neural networks. I think of it like a deeper level of pattern recognition. It can automatically extract really complex features from the data without being explicitly told what to look for. And it can integrate multiple types of models. This is crucial for TCM. One big challenge was figuring out if a compound activates or inhibits a target, especially when you have dozens of compounds acting on hundreds of targets simultaneously. It gets ambiguous fast.
Right, the activation versus inhibition problem. How does DL address that?
So there's this model called HTINet2, specifically designed for TCM. It's pretty clever. It doesn't just look at molecules. It builds what's called a knowledge graph. This graph includes not just the chemical data, but also the traditional TCM properties of the herbs, things like its nature, hot, cold, its flavor, sweet, bitter, its meridian tropism, which organ system it's thought to primarily affect.
Wait, hold on. It's incorporating concepts like meridian tropism. That sounds subjective.
Sure.
How does that work without just encoding old assumptions?
That's a fair question, and a really important one. The goal here isn't necessarily final validation at this stage. It's about smarty hypothesis generation. It uses something called knowledge graph embedding to translate these TCM concepts into the model's understanding. Then, a part of the model called a residual graph convolutional network, or GCN, uses this context. Basically, it tells the AI, look, based on centuries of observations suggesting this herb affects the liver meridian, it's more likely to interact with targets related to liver function. It helps the AI focus its predictions, making them more relevant to the known effects of the herb. It significantly outperforms generic models that ignore this prior knowledge.
Okay, so it's using the traditional knowledge as a kind of guidepost for the AI's exploration. Interesting. Let's shift gears slightly. From the lab bench to the clinic. AI isn't just analyzing molecules, it's also tackling the really subjective parts of diagnosis, right? Like looking at a patient's tongue.
Yes, this is a huge area. Tongue diagnosis is a cornerstone of TCM, but it's famously reliant on the practitioner's individual experience. Highly subjective. So researchers use deep learning, specifically a model called LGN Label-Guided Attention Network. They fed it tongue images from 165 stroke patients. The AI learned to classify complex features, subtle color changes, the thickness and color of the coating, signs like ecchymosis, which are like little bruises, and it achieved really impressive accuracy, over 81% macro average accuracy. The key was the attention mechanism.
Attention mechanism, like it knows where to look.
Exactly. It's like the AI learned to focus on the parts of the tongue image that are most clinically relevant, mimicking how an experienced physician would scan the tongue. It highlights specific areas, the sides, the root, the coating texture that correspond to different TCM syndromes. It turns that visual subjective assessment into quantifiable objective data points. That's a major step towards standardization.
Fascinating. From images to words, what about all the text? Millennia of ancient TCM texts, plus messy modern clinical notes. How do you turn that into structured, usable knowledge?
That's where large language models, LLMs, come in. You've probably heard about models like GPT. Similar principles apply here, but trained specifically for medical and TCM contexts. Think of models like MedChat-CH. The first step is just collecting vast amounts of text data, ancient classics like the Huangdi Neijing, modern research papers, and crucially, tons of unstructured electronic medical records, EMRs.
Those EMRs must be a challenge. Different doctors, different phrasing, maybe even archaic terms mixed in.
Absolutely. That's where the LLM shines. It can handle heterogeneous data. It can learn to translate ancient Chinese phrasing into modern terms. For the EMRs, techniques like Doc2Vec are used. Doc2Vec basically converts blocks of text, even vague descriptions like patient feels heavy or discomfort in the chest, into numerical vectors, mathematical representations.
So it turns subjective descriptions into numbers the AI can actually work with.
Precisely. Instead of just words, the AI gets data points it can analyze. MedChat-CH can then extract the core relationships, the symptom-syndrome prescription triad, with remarkable accuracy. It builds a coherent knowledge network out of all this previously disconnected information.
Okay, so we've got AI handling complex static data with MLDL and unstructured text with LLMs, but you mentioned network pharmacology was static and the real biological system is dynamic. What's the next frontier for truly understanding how these multi-component formulas work over time inside the body?
That frontier is AI-integrated virtual cell models, AIVC. This, I think, is the real game changer for cracking open that mechanistic black box of TCM synergy. The core idea is to build dynamic simulations of biological systems, cells, tissues, and a computer. It allows us to model the multi-component, multi-target spatiotemporal efficacy of TCM. Spatiotemporal meaning how effects unfold across space and time.
A virtual cell. That sounds incredibly complex to build, like SimCity but for biology. How does that even work?
It is incredibly complex, built layer by layer. Step one is creating universal representations. Think of it as defining the fundamental building blocks. At the molecular scale, you model the key players, DNA, RNA, proteins, often using techniques similar to LLMs but adapted for biological sequences. Then at the cellular scale, you integrate data like transcriptomics, which genes are active, and proteomics, which proteins are present, to create a unified digital representation of a specific cell type.
Okay, so you have the basic cell blueprint. Then what?
Step two is the multicellular scale. A cell doesn't exist in isolation, right? It's part of a tissue. So you use techniques like graph learning or sophisticated neural networks, CNNs, transformers, to model how cells interact with their neighbors, how signals pass between them. For stroke, this means modeling neurons interacting with inflammatory cells, for example. And the final piece is creating virtual instruments, or VIs. These are like digital tools you use on your virtual cells. You have manipulator VIs that let you simulate an intervention, like adding a specific mix of herbal compounds to the virtual environment. And decoder VIs that predict how the cell's state changes in response, what genes turn on or off, what proteins increase or decrease.
So you can actually simulate administering a TCM formula to a virtual nerve cell damaged by stroke and watch digitally how it responds over time.
That's exactly the goal. You can simulate the reparative effects, the anti-inflammatory actions, the interactions, translating TCM's dynamic synergy into something quantifiable and observable. Even if it's in a simulation, it's a whole new way to generate and test hypotheses about how these complex mixtures work.
Amazing. So if we put all these AI tools together, ML, DL, LLMs, and now AIVC, what does the overall research process look like? Is there a new standard framework?
Yeah, there's a theoretical framework emerging. It starts with the input data, all the omics data, chemical structures, maybe even spectral data from analyzing herbs. This feeds into the AI tool chain, the GNNs, LLMs, ML algorithms we've discussed. They process this data. The output from the AI is a specific testable hypothesis. For example, we predict compounds A and B from this formula synergistically target the NFB pathway to reduce inflammation. Okay, and this is crucial, that hypothesis then goes through multi-scale validation. You don't just trust the AI.
Right, you have to prove it in the real world.
Exactly. First, maybe more computation, like molecular docking simulations.
Mm-hmm.
Then testing in the AIVC models. Then moving to traditional lab work in vitro assays, like Western blots, to actually measure protein changes in real cells.
Mm-hmm.
And finally, in vivo testing in animal models, like the standard MCAO model used for stroke research. The AI proposes, the lab disposes, essentially. It's a powerful cycle.
It sounds incredibly powerful, a real fusion of computational and experimental science. But we have to address the challenges. What are the big roadblocks still standing in the way of fully integrating AI and TCM, especially for something like stroke treatment?
There are definitely significant hurdles. The first, and maybe the biggest, is data quality and standardization. TCM data is inherently complex and often subjective. Think back to that tongue diagnosis study. The AI was trained only on images from one hospital, the Hunan Provincial Hospital of TCM.
Which means it might have learned biases specific to how that hospital's practitioners interpret tongues, right? It might not work as well elsewhere.
Precisely. Institutional bias is a huge risk.
Yeah.
Training AI on limited or fragmented data is like trying to understand global weather by only looking at the forecast for one town. We desperately need large, multi-center data sets collected using standardized protocols. Getting different institutions to agree on and use the same methods for things like pulse diagnosis or syndrome differentiation, that's a major challenge.
Okay, data standardization. What else?
The second major issue is model interpretability. Many of the most powerful AI models, especially in deep learning, are effective black boxes. They give you an answer, but it's hard to see how they reached it. This clashes fundamentally with TCM's philosophy, which emphasizes logical coherence, the principle, method, formula, medicine chain of reasoning. Doctors need to understand the why behind a recommendation to trust it.
So the AI needs to be able to explain itself in terms a TCM practitioner can understand and accept.
Exactly. We need more development in explainable AI or XAI techniques that can map the AI's prediction back to established TCM theories or understandable biological mechanisms. Building trust is key for adoption.
Makes sense. And the third hurdle?
Clinical translation. Getting these models out of the lab and into real-world clinical practice. This involves so many steps. You need rigorous validation in independent patient groups, real-world validation, or RWV. You need to navigate complex and constantly evolving regulatory landscapes, getting approval from bodies like the NMPA in China or the FDA in the US for AI software as a medical device. And because TCM treatment is highly personalized, beyond saying Lunzi, treating based on pattern differentiation, defining the precise intended use of an AI tool for regulators can be tricky. Plus, you need to prove cost effectiveness. It's a long road from a promising model to a tool doctors actually use daily.
So the path forward involves not just better tech, but also better data practices, building trust through transparency and navigating the practicalities of healthcare systems.
Absolutely. Multi-center data, standardized collection, explainable models, and robust clinical validation strategies are all essential.
It feels like we're right at the cusp of something transformative, though. This combination, LLMs handling the vast knowledge base and AIVC simulating the dynamic biology.
It really is. We're shifting TCM stroke treatment from being primarily based on historical, empirical summaries toward a future of precise, individualized, and scientifically validated therapies. The potential to accelerate the discovery of new drugs derived from TCM principles and to create truly personalized treatment plans based on both AI analysis and TCM wisdom. It's enormous.
It definitely is. Okay, let's leave our listeners with a final thought to chew on. We've talked about how AIVC might simulate the complex dance of molecules in a cell responding to a multi-component TCM formula. Considering this rapidly advancing tech, how close are we really to being able to precisely quantify that core TCM concept of synergy, the Junchen Zuoshi principle, where different herbs play distinct cooperative roles like emperor, minister, assistant, and messenger? Could we soon digitally model and measure how those roles combine to create an effect greater than the sum of its parts? Something that seemed like pure philosophy just a few years ago might be on the verge of becoming quantifiable science. What does that mean for the future of medicine? Something to think about. We'll catch you on the next deep dive.